Hi, my name is Brian, and this is my lab three black holes. I guess the first part of it was finding the mass of the black hole, right? We were given a lot of givens, I guess, or a lot of values for the variables in the universal law of gravitation, right? We were given g, we were given the mass of the star one, and we were given delta r, right? The star's position in the code was just automatically constantly being updated, given the velocities. And yeah, our goal is to just find the mass of the black hole here. We found FG by adding up the parallel and perpendicular components of dp over dt, right? Because as we know, F net is equal to dp over dt, assuming all FG is the only force in play here. Um, Obviously, we could find the parallel component, just by essentially finding the rate of change of the magnitude of I'm sorry, the rate of change in the magnitude of the momentum, and multiply that by the parallel vector, right? This code lays out all the steps here. You have the initial velocities that were given, right? You can use that to find the the initial and final momentums, which again, that you can measure a change there, right? That gives you dp over dt, and yeah, obviously, f net is equal to dp over dt. And once you have dp over dt, you could obviously get the magnitude of you can measure the change in the magnitudes of the initial and final momentums to find the parallel component. And once you have the parallel component, you obviously just subtract that from dp over dt, which is equal to the net force, to get the perpendicular component. So yeah, once you have both components, now you know fg, right? Now you have all the variables you need, right? And plug in all the variables, and you could find out the mass of the black hole, which I got to be 1.31 times 10 to the ninth. And I could show you the model here. And essentially, if you guys can look at the arrows here, right? There are three arrows, one that's very tiny and pink over here, and the two that are, getting larger and smaller depending on where the star is relative to the black hole, right? The parallel component is very small, almost negligible, whereas the perpendicular components and just net force in general, right? It's pointing towards, right? It's pointing towards the black hole, right? Because there's a gravitational pull that the black hole has on the star, right? And it gets bigger because as distance decreases, the pole gets larger, right? I think what does it mean, right? I guess the question we ask here is like, what is the difference between that force and the rate of change of momentum, aka dp over dt? And while they may have equivalent values, right, F net is equal to dp over dt, they're not exactly the same thing because net force is essentially the sum of all forces. The net force tells a story about all the forces that are acting upon an object, right? And we measure that force by the effect it has on an object's motion, right? dp over dt tells a story of the motion, right? Not It doesn't tell a story about the forces. It says nothing about whether gravity is acting upon it, whether there's a normal force or spring or tension. It just describes, you know, what the object is going through, right? It's an analysis of what happens or analysis of the object's kinematics. So essentially, yes, they may be equal in value, but they measure different things. Part two, oh, sorry, part two of the lab was escaping the black hole, where we had a spaceship and we wanted it to uh, kind of braze or graze the black hole and you know but at the same time blast past it, right? We were given, I guess, all the masses, right, of the black hole, the planet, and the ship, right? And we wanted to find all the forces acting upon the planet so we could see, we could measure the planet's kinematics. We also wanted to find all the forces acting on the ship so we can find, the initial velocity that the ship needs in order to just blast past the black hole, right? Whenever we find the forces, right, we would update the ship and the planet's velocities and positions, one after the other, right? And once that happens, you could kind of guesstimate a ship's initial velocity in order to be this. Uh, I could show you. Oh yeah, this model kind of shows, I guess, a ship's path, right, or a ship's trajectory. It like barely grazes the black hole, right, without actually crashing into it, and just leaves the system at the same time, which is what we wanted. Obviously, just a little bit on these two. This is the velocity update formula, and you could update the position if the final velocity, because in a non-contact force environment, we could estimate v average to be vf. Yeah, this code kind of just shows essentially how everything works, right? You would find the distance between two of the objects, whether it's black hole to planet or planet to star or spaceship, right? And yeah, once you have the distance, you just plug in all the masses and g, and then boom, you have the forces. You have the net force, right? Which you can then use to update the velocity and the position. I guess the question we could ask is that what if you wanted to orbit the black hole instead of blasting past it? I think one thing to note is that the ship and the planet weigh way more than the black hole, right? The black hole was like 10 to the ninth kilograms, whereas both the ship and the planet are way above 10 to the 20th kilograms, uh, which kind of signifies the pole of the black hole might not be enough to draw the ship towards it, right? And we would need the initial velocity of the spaceship, right? Assuming it, loses power around where the black hole is, right? The initial velocity will have to still be high enough to escape the planet's gravitational field, right? Which is going to be huge, but low enough to the point where it won't just zoom past the black hole. And just from the numbers that I plugged in, I've kind of figured out that that wasn't possible, or there wasn't an initial velocity that allows the spaceship to orbit the black hole, right? And my thought process was maximizing, gravitational pull between the black hole and the spaceship, right? By decreasing the distance as much as possible. And yet, I just couldn't really find that initial velocity. But yeah, that's mostly it. And thank you for listening in.